Welcome to a new video. In this video we will discuss the QR factorization. We have seen in the previous video about the Gram-Schmidt process in order to create an orthogonal basis from a set of vectors. And this QR factorization, which has an application in the numerical approximation of eigenvalues. Of course, we will see that step by step in our calculations and also verify these in MATLAB command window. Okay, now the objective is we like to determine the QR factorization of this matrix. We have seen also this matrix in the Gram-Schmidt process. So how the process of factorization works? Let's first write down our equation we need to use. We need to say that the A is decomposed or factorized in the Q and R. So there is a matrix Q which has orthonormal columns. We will calculate that shortly. And we have also this matrix R, which is an upper triangle matrix. We will see that shortly what it all means. Okay, let's go first to the calculation. Step one is we create or denote our columns here as vectors. So we denote the columns of the vectors, the matrix A, as these three vectors. So we call it, for example, x1, x2, and x3. Now the next step is using the Gram-Schmidt process to form an orthogonal basis using these vectors. Okay, now we again set the vector v1 as x1, that is the Gram-Schmidt process step 1, and then we calculate the second vector v2, which is then the x2 minus the projection formula we have used in the previous example. Now you see that we need to use the v1 and also the dot product of the v1 in itself, and also dot product of v1 and x2. Now those are calculated here, so v1 dot product with x2, that is calculated like so, so this is just multiplication in the two vectors. So 1 times 2, 1 times 1, and 1 times 3, so the result is 6. In a similar form, v1 dot product with v1. Okay. Now we need to now substitute that in here, so we have here now make the vector x2 and the 6/3 and our vector v1. Now the result is shown here, and that will be then 0, -1, and 1. Now the calculation of the vector v3 goes in a similar form, but now we need to also use an additional subtraction to get the orthogonal vector v3. Now we need to use the x3 and then multiply that in the same fashion as we have done it here, but then specific with the x3. Again, let's calculate the dot products here, because we need to do v1 dot x3. We also need to do v2 with the x3, and we also need to do x2, the v2 and v2 itself. So one by one, the calculations are shown here. So again, the dot product of two vectors goes like so. So we have here now the results. We just substitute the values from here, and we get our result here, which is now our third vector. Now we can create the orthogonal basis from these three vectors. We have now formed v1, v2, which is this one, and v3. So these three vectors will now form an orthogonal basis. Of course, we need an orthonormal basis. It means we need to normalize these vectors. That will be then done shortly. Okay, now step 3 is we need to now construct our matrix Q. That is the matrix we were talking about. So we will now also say that the matrix Q will contain orthonormal columns, which are formed from the columns we have originally from matrix A by going to the Gram-Schmidt process, and now we need to do the normalization. Okay, now the Q again will be have three columns, Q1, Q2, and Q3. These are the columns we need to calculate, so these are the three vectors we need to calculate. So normalize each vector we have determined in step 2. So we say the normalization of the v1 goes like so. So we do 1 over the length of the v1 times the v1 itself. That's shown here. So we just take the length, 1 over the length times the vector itself, and that's shown here. So 1 over the square root of 3 for all of them is exact same. Now for the Q2 we need to take the length of v2. So 1 over the length of this one times the v2 itself, that's shown here. So 0 squared minus 1 squared and 1 squared, that is in the denominator here, and then you get the vector v2, and now we get the result. Similar form for Q3. So again, we normalize this by 1 over the length of the V2 times the V2. V3, I mean. So 1 over the V3 times the V3. That's all shown here. Now we have our Q1, Q2, and Q3, so that can be substituted in here, and that goes like so. Okay, now we have our matrix Q also. The next step is calculation of the matrix R. Now, step 4, construct the matrix R. So we know that since this matrix Q is an orthonormal matrix, so it has orthonormal columns, we can say the following. Now, since Q has orthonormal columns, that is the condition. If you have that, that means the transpose of that matrix times the matrix itself will be an identity matrix. It can be proven, but this is the identity matrix, and we can use this condition. So we can write that the A is equal to QR as we have it in the original equation. We can multiply now this equation on the left side here with a Q transpose, and also here on the left side with Q transpose. Now, since Q transpose Q is an I, which is an identity matrix, and identity matrix times the matrix R will be just R. So we have now our formula for the matrix R, which is Q transpose A. So what is Q transpose? We need to create the columns from these rows. So we take this row 1 and we make a column. We take the second row from Q, we make a column. And we take the third row of this and we take a column. Now we can calculate the matrix R using the formula here. So Q transpose A, Q transpose in here, the matrix A in here. Now we do the first row times the first column. So you do element wise 1 over the square root of 3 times 1 plus 1 over the square root of 3 times 1 and 1 over square root of 3 times 1. So you add them up. Then you get now 3 times 1 over the square root of 3. That means 3 over square root of 3. And then you do that actually in the similar form for the first row, second column, first row, third column, etc. Now you get again a 3 by 3 matrix. Now since 3 over square root of 3 will be square root of 3, effectively that is the result. And now you get here the complete expression by also simplifying these expressions. Now you see here indeed that the R, matrix R, is an upper triangle matrix. Okay, now we have the Q and the R. Now we can also check that it is indeed correct, because this needs to hold. QR must be A. So we have here our Q, which is then from this expression. And we have our R here, which is our matrix R. Now we need to do matrix calculation again. So the first row, first column, first row, second column, etc. If you now do that procedure one by one, let me show this first left top value. 1 over the square root of 3 times the square root of 3 will be 1. And then you get here 0 times 0 plus minus 2 over square root of 6 times 0, so you get exactly 1. So this is indeed correct. Okay, let's also go to the MATLAB. So collect here the Q and R we have calculated. This is now the MATLAB command window. We define here the x1, that is the vector x1, vector x2, and vector x3. That's actually just the vectors from the columns of matrix A. Now we set up our matrix A in the MATLAB, and then you can type this command QR parentheses A, and then you do here in the brackets Q comma R. Then you create here the values for the Q matrix and the R matrix. So we have now the calculation of the QR factorization. Okay, now this is calculated by the MATLAB Q, and this is calculated by the MATLAB as the matrix R. Now there's an interesting thing happening here, because if you look at this Q and this Q, it's a little bit different because the values are here all minuses, so the exact same, actually rounding off. But we have the positive signs here, and the rest are exactly the same. And you also have that for the R, because of this, the R will change, and you see here this is all the same, only the sign is reversed. And the rest of the parameters are exactly the same. Now what happens here? You might say we have it maybe calculated wrong. No, the thing is, QR factorization is not unique, and we have checked our QR factorization, that was actually correct. So, and this is also a possible QR factorization with this Q, which is of course having a different R, so that's also valid. So this is indeed no problem, and the QR factorization is correct. All right, we have discussed the QR factorization for this matrix, and we have shown the steps in order to go to the matrix Q and the matrix R and verify this in MATLAB command window. See you next time in another video.